Up to this point, we have discussed various growth pathways indirectly related to muscle protein synthesis with regards to the use of BFR. You might be wondering, is there an actual signaling pathway that is directly related to muscle protein synthesis? When talking about muscle protein synthesis, it's important to be familiar with a basic formula. In order to support muscle hypertrophy, there must be a positive net protein balance. Net protein balance equals muscle protein synthesis minus muscle protein breakdown. When your protein synthesis exceeds your protein breakdown, you have a positive net protein balance. And if you have protein breakdown that exceeds your protein synthesis, you're looking at a negative net protein balance. Most of us are aware that we need protein supply for our bodies to synthesize in order to increase muscle mass or hypertrophy. It is no surprise why protein bars and protein drinks are very popular with people who are working out to build muscles. Muscle protein synthesis is seen within 24 hours after a heavy bout of resistance exercise. Now that we are familiar with this basic formula, let's go back to the protein synthesis pathway. Scientists have learned that the signaling pathway responsible for protein synthesis and ultimately hypertrophy is known as mTORC1. It stands for mammalian target of rapamycin complex 1. Sometimes the term mammalian is replaced by the term mechanistic. Rapamycin is a drug used to stop protein synthesis and cell growth in tumors, and is used as an immunosuppressant. It was named after the native name of Easter Island, which is Rapa Nui. It's where scientists have discovered a bacterial strain that secretes a compound that binds to a protein in our bodies. Later, it was discovered that binding to this protein serves as a switch to turn cell growth on or off. So binding to this protein can stop protein synthesis and cell growth, which is why it became a potent immunosuppressant to aid in organ transplants, since the drug was created out of the rapamycin bacteria. This particular protein was given the name mammalian target of rapamycin. A study has demonstrated that rapamycin blocks mTORC1 and protein synthesis after exercise and ingestion of amino acids. Another study found that taking muscle to failure, either by increasing loads or repetitions, will activate mTORC1. But is mTORC1 dependent only on heavy loads or exercise to failure? In a study by Gunderman and colleagues, they have demonstrated that muscle protein synthesis associated with BFR and exercise is directly tied to the mTORC1 pathway, which offered more evidence supporting the actual mechanism that increased muscle protein synthesis after BFR. Their findings contradicts the old paradigm that mTORC1 activation is dependent only on heavy mechanical loading, and that very low load will not be able to induce this pathway. In their study, two groups of patients performed BFR at 20% of 1 RM. The experimental group took the drug rapamycin, and the control group did not. At the end of their study, they were able to show that rapamycin taken by the control group was able to block the mTORC1 muscle protein synthesis, since this group did not show any significant changes in muscle protein synthesis and mTOR markers compared to the group that did not take rapamycin after performing BFR and exercise. This is a true paradigm shift in our understanding of exercise and muscle protein synthesis. Previously, we only know that muscle protein synthesis is dependent on load. that we have to work with 70% of 1 RM in order to induce hypertrophy. But now, we have evidence supporting a new paradigm, one that shifts the focus from mechanical load and into substantial anaerobic metabolism that facilitates recruitment of larger, fast motor units, and BFR may play a key role. Is BFR able to activate the mTOR pathway, much like lifting heavy? Another study measured the effects of BFR at 20% of 1 RM versus work match controls and found at the completion of the session that only the BFR group demonstrates a significant rise in ribosomal kinase, a downstream marker of the mTOR pathway, which translates to increased muscle protein synthesis. What about the elderly who are unable to lift heavy? There is a gradual decrease of the ability to process protein as we age, leading to gradual loss of muscle mass, strength, and fiber size. It is called sarcopenia. Think of Arnold in his prime. My bet is, he didn't stop working out, but he still lost muscle mass because he was aging. We all do. As it turned out, a study already examined the effects of BFR on muscle protein synthesis in older men and found that mTORC1 and protein synthesis increased in the BFR group but not in the control group. Since we now know what serves as the switch for turning cell growth on and off, where are the signals coming from? Signals come from growth factors. We have discussed these in previous videos. Signals come from cells' energy status. We need to have potential. As long as our cells are alive, it has potential, though it may vary based on how old and how healthy those cells are. Signals come from protein supply. We need to have supply of amino acids as building blocks. And finally, signals come from exercise. We need to have an adequate training stimulus. As we have learned, if you can't lift heavy, whether from an injury, from surgery, or from old age, BFR has the potential to induce adequate training stimulus to switch on the mTOR pathway. For more information, I go to owensrecoveryscience.com. There is where I find any relevant information regarding the use of BFR for my clinical practice. There, you can also find BFR certified clinicians near you. If you want to see more videos and information about BFR training, please leave a comment and check out my other videos. And don't forget to click the like and subscribe buttons. Thank you for watching.